Welcome to homework.
Again, we are asked to compare the electric force and the gravitational force between an electron and a proton in a hydrogen atom if they're separated. Let's write it down. Hydrogen atom, if they're separated by 0.53 times 10 to the power of negative 10 meters. Okay, so you can imagine, in the hydrogen atom, in the nucleus, you have a proton, right? And around the orbit, we have an electron. Then we're giving this distance as r. So we can calculate easily, right? We can calculate the electric force between the two. So the first thing to remember, proton has a charge of a positive E, which means it is 1.602 times 10 to the power negative 19 coulombs. For an electron, though, although it has the same magnitude of charge, as you know, it is a negative charge, right? However, the sign is not going to matter here because we're looking for the magnitude of the force, not the direction necessarily. So we're basically looking at the absolute value of the electric force. So K, let's start with the generic equation, the distance between charge Q1 and Q2. Now, if we specify it for this circumstance, let's say, for the proton, we have positive E, right? But for electron, we have negative, so we have to take the absolute value of it because, again, in the left-hand side, we're trying to figure out the magnitude of the force. So in denominator, R12 is simply going to be equal to our R squared. So K E squared over R squared, E being positive, is going to give us the magnitude of the electric field. So then if we plug in the values, K is 8.99 times 10 to the power of 9 Newton meter squared per coulomb squared. So the E positive 1.602 times 10 to the power of negative 19 coulombs, but we're going to square it. And in denominator, we have 0.53 times 10 to the power of negative 10 meters. We're going to square this. Now, then the magnitude of the electric force between a proton and an electron is going to be 8.21 times 10 to the power of negative 8. Right? This is the magnitude of the electric force or Coulomb force, whatever you want to call it. Now we can calculate the gravitational force between the two as asked in the problem. So it's going to be very similar, right? G, this time gravitational constant, times the first mass, times the second, divided by the square of the distance between the two. So for our case, let's remember a few things. Let's say M1, just like we did here, M1 is representing the mass of a proton. Let's write it here. You can find this in any textbook. The mass of a proton is 1.67 times 10 to the power of negative 27 kilograms, and mass of an electron is 9.11 times 10 to the power of negative 31 kilograms. And the value for G is 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. Now, if we plug everything in our force equation, then we have 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. M1, the mass of a proton, 1.67 times 10 to the power of negative 27 kilograms. Mass of a electron is 9.11 times 10 to the power of negative 31 kilograms. And in denominator, we have still the same radius, right? 0.53 times 10 to the power of negative 10 meter squared. Now, then they may put it here, the F sub G, let's separate this. Pardon me, this is pretty cramped up. Okay, I'm going to do it on the next page. All right. Never mind this. So the magnitude of the gravitational force then is going to be equal to, from that calculation on the previous page, 3.61 times 10 to the power negative 47. Look how small it is. Now, if we take the ratio of the electric force to the gravitational force, then let's remember what electric force was, 8.21 times 10 to the power negative 8. 8.21 times 10 to the power negative 8 divided by 3.61 times 10 to the power negative 47. So this ratio is going to be huge, right? 2.27 times 10 to the power 39. So 10 to the power 39 is a very big number, and you can see how strong the electric force is compared to the gravitational force. So the gravitational force that they're exerting on each other is technically negligible if we're talking about the Coulomb force, right? It's very small.